Excuse me, I'm going to sneak past the shoulder here. I took your chair. Thank you. Well, good afternoon once again. I'm sure you've all noticed I wrote up here the homework assignment that's due next class. Now this is a little bit awkward because in breaking down the big textbook into two parts, Dr. Durando took the stuff that we're talking about now and put it in his portion. So this chapter 16 is really in the last semester's textbook, which I'm hoping that you all have. If you don't, see me after class and we'll talk about some options as to what we can do about that. So anyway, here's one of the problems from that book and a couple parts of it and a little more thing to do with it about confidence intervals. As a general rule in writing up homework problems, I don't want you to write too much. I mean, that's almost a no-no, I would say. If you're in a business situation, if you're looking for a group of people or a company, they don't want you to write all the details that you thought about in your reports. They want the main things said, and if there's some detail that you think is necessary, you can put it at the end in the appendix, for example. It doesn't have to be in the flow of the whole solution. So for example, I would think that problem there could fit on one side of my page. Just to give you some idea as to what I'm talking about there for the length of what you write for homework. The next thing before I forget, I have a class list printed out here, and what I'd like to do is just let this circulate through the group here and check it off on the left over here if you're here. If you're not here, don't check it off. Oh, the other things that I passed out to you, the thicker one, the first one was the copy of the table of contents of the big book. So this starts with chapter 1 and ends with the last chapter, whatever number it is. But I thought this detailed list of the topics in each chapter was useful. And I noticed in our textbook, for example, this isn't in it. So maybe that's something we should fix for another semester. Right? So anyway, I thought this might be of some use to you to see the detail that's in the various chapters of that text. And the other thing I passed out was basically an F table and a T table. So there's 2 pages for an F table and I believe 1 page of a T table. The tables are in your textbook, but I thought maybe having an extra copy like this might be handy. When you're in class, for example, you didn't have a textbook with you, you could be carrying a single page like that. Or for your own work, or for tests, for example. You use that for your tests. So anyway, an F table and a T table there should give some use. Well, last time I was talking about this one-way, one-factor analysis of variance problem, and I'm realizing that this is a review for many of you, and still I want to go through it in some detail because it sort of forms the basis for things that we'll do as we go on a little further. But I had forgotten the last page of this handout, page 12 of 12. So let me start there today and take a look at the items that are here. What I tried to do here in this last page was basically to summarize some standard results out of mathematical statistics, and they're the kind of results that we use throughout this class, for example. Although our emphasis is not going to be on proving things upon theory so much, but on occasion I can make some brief remark about what a proof might look like for a given thing that we're talking about. So some of these things that are hopeful that you see before. B is any random variable and any linear constants. What's the expected value of such a linear function? Well, it's just that. What's the variance of such a linear function? Well, the B has no effect. The A comes out as a square. If mu is the mean of V, and sigma squared is the variance of V, then this standardized variable, V minus V over sigma, is mean 0 and variance 1. And that's true for every random variable. It doesn't have to be a normal distribution or anything like that, for instance. So upping up again to number 3, if V1 and V2 are random variables, V1 and V2 are just constants, then what's the expected value of this linear combination of the 2 variables? Well, there it is. Expectation of the separate terms, and then you come back and apply this idea right here to write the last pieces. What's the variance of this kind of thing? Well, there's the formula. Notice how the coefficients are squared. We get the variance of one variable, the variance of the other variable, and then in general, there's a covariance piece, the covariance between the 2 variables. If 2 random variables are independent, then their covariance is 0. So in that case, is the case we're going to be most often encountering, this piece drops away, so we can have it. These are written for the case of 2 variables, but if we had 3 variables or 4 variables or 5 variables, we do the same thing. Then, number 4, if x is normal 0, 1, the n stands for normal there, then x squared has a chi-square distribution with 1 degree of freedom. If x is normal near 1, unless they got mean near 1, then x squared is chi-square 1 delta. This is my notation for a non-central chi-square distribution. There's 2 parameters in it, the degrees of freedom and what we call a non-centrality parameter. And the value for the non-centrality parameter follows the rule substitute in the mean. So if this is the variable we're talking about, to get the non-centrality parameter, you substitute in the mean of x, and you get mu squared is the non-centrality parameter. So that rule carries over into higher order cases as well for non-central parameters. Non-centrality parameters, I should say. But if we have a collection of independent random variables and each is chi-square, let's say r degrees of freedom for the ith one, then the sum of these variables again has a chi-square distribution, and the degrees of freedom are the sum of the individual degrees of freedom. So the sum of independent chi-squares is again chi-square. 6 says officially how we define a t distribution, a t random variable. So we take a variable which is normal 0, 1, and another variable which is chi-square with r degrees of freedom, and thirdly they're independent. Then if we form this quantity, v divided by the square root of v over r, this variable has a t distribution with r degrees of freedom. So that's how a t distribution is defined. So we go on. V1 is chi-square r1, V2 is chi-square r2, V1 and V2 are independent. Then if we form this ratio, V1 over its degree of freedom divided by V2 over its degree of freedom, and this has an F distribution with those two degrees of freedom. So this is how an F distribution is defined. So it's a ratio of two chi-squares. All right? V is non-central chi-square, r degrees of freedom, delta non-centrality parameter. Then the expected value of V is the sum of those two parameters, r plus delta. Properties theorem says if we have V equals V1 plus V2, V is chi-square with r degrees of freedom, V1 is chi-square with r1 degrees of freedom, and V2 is greater than or equal to 0. So if we have this kind of setup, then we can conclude that V2 is also chi-square with degrees of freedom r minus r1, so that they're matching up on both sides of the equality. And moreover, V1 and V2 are independent. So that's called properties theorem. Lastly, given a collection of independent normal random variables, then these are the standard results. Y bar has this distribution. I think I talked about that last time. N minus 1 s squared over sigma squared has that distribution. I think we used that last time as well. And moreover, y bar and s squared are independent random variables. So if we were to use this information, for example, in combination with the, where do we go right here, the t distribution, you could do something like this. Let's suppose we're in the context there of the last line, number 10. So if we take y bar, subtract off its mean, divide by its standard deviation, from one of our remarks earlier here tonight, that's normal 0, 1. So if we divide that by the square root of the chi-square 1, n minus 1, s squared over sigma squared, and divide that by its degrees of freedom, which is n minus 1, then this variable has a t distribution. Now you do a little bit of algebra on this. You can cancel out the n minus 1s down here. You can cancel out the sigma squared, and you're basically left with y bar minus mu over s over square root of n, like that. So that's the variable we call the t variable. So sometimes people get to this t distribution by saying, well, it's like the first one, the normal one that I wrote down there. but you just replace sigma by s and then you get a t. Well, that's sort of the way it works out in the end, but that's not a proof. That's not an argument for that result at all. This thing has a t distribution because it matches the pattern. Oops, I'm taking it down. The pattern for a t distribution. When we were talking about something last time, let me see, finger on something here. Here on page 3. On page 3, down here near the bottom in point 5, the 95% confidence interval for uj is given by that formula. Well, where does that formula come from? It comes from the form of the t random variable. For instance, if I go back to here and say, let's find a number from the t table. Let's just use a specific number. So that that's true. Now substitute in this for t, right in there, and then do a couple algebra steps to isolate mu alone in the middle. And you do those 2 steps, actually, they are. You'll have mu isolated in the middle, but on the upper end, you'll have y bar plus t.025 s over square root of n. And on the lower end, you'll end up with y bar minus t.025 s over square root of n. So that's how we derive the confidence interval formula for mu. It comes from this t distribution type stuff here that we're talking about. We're going to encounter such confidence intervals many times over the course of this semester, and we're not going to repeat this kind of an argument each time we encounter it. But I'll just mention occasionally, hey, this is derived, this is verified by this same thought. We start with a t random variable, and then we do this move to form the confidence interval. Okay? Stop me and ask any questions you want along the way. Stoppable in that sense. Still looking on page 3 at number 2. Sum of squares error over sigma squared is chi squared n minus k. Now I seem to recall having made a brief proof of that, showing that this random variable here is the sum of k chi-square random variables, and so it was a short argument to come to this conclusion. So to prove that, what I was really using was something that's on the last page here, number 5, which says if you have independent variables that are chi-squared distribution, then the sum is also chi-squared. So that's the result officially stated there that I was using in that proof. Now, let's come to this analysis of variance table on page 2. We have an F statistic here. Why does that have an F distribution? So that's the question I'm asking, and kind of verify it from some of these principles we've just talked about. So the way this would go would be like this. from what we had proven before, sum of squares error over sigma squared is chi squared with n minus k degrees of freedom. Now, what I would do would be to come in here to this remark, slide a sigma squared in the denominator of each part, like that. And then I know the distribution of this variable on the right. So what I want to do is to come to the variable on the other side of the equality, the sum of squares total over sigma squared. So let's look at that. Where can I slide it? I guess I've got enough room to write it down here. Sum of squares total, t, over sigma squared is double sum of yij minus y bar double dot squared divided by sigma squared. Now the yij's here are normal with mean something, mu j would be, and common variance sigma squared. Okay. Now when I look at this expression, what it reminds me of is even though I have doubly subscripted y's, this numerator expression looks like a sample variance. It looks like a sample variance of all the y data. Consider them down the columns, across the rows. There's a collection of variables, normally distributed variables. They all have the same variance. They're independent. And this numerator looks like the formula for a sample variance. So what I'm looking at here is basically something that looks like an s squared over sigma squared. And we had said that that kind of thing is going to have a chi-square distribution. And it's going to have a chi-square distribution, and for a sample variance, the degrees of freedom are 1 less the number of variables. So it would be n minus 1. So there's the thought. That expression right there, sum of squares total over sigma squared, being like a sample variance over the population variance, would be chi-squared with n minus 1 degrees of freedom. But there's something missing here. These yij's don't all have the same mean. They have differing means. So that's the bugaboo in the story. So what we do basically is to say, well, this doesn't end. There would be a non-centrality parameter. And the non-centrality parameter would be gotten by replacing each of the yij's up here in this expression by its mean. So we could plug it in and get an expression for that, but we don't need it for any purpose, so I'll just say it's there, and you don't have to specifically look at it and use it for anything. The point is that it's chi-squared with some non-centrality parameter. So now, if I come back to, where was I writing? Right here. I know this one is chi-square. I know this one is chi-square. I know this one is, whatever it is, it's greater than or equal to 0 because it's the sum of squares of things, negative. And so then I pull up Cochrane's theorem. So I'll have to pop that in front of your eye here. That was on the very last page. It was number A9. Okay. So here we have an A9. V is V1 plus V2. We have that format. V is chi-square. V1 is chi-square. And then the other variable is greater than or equal to 0. So in that case, we can conclude that the remaining variable has a chi-square distribution, and the V1 and V2 are independent. So if you, by the way, this Cochrane's theorem here is written without non-centrality parameters in it. if these chi-square variables had non-centrality parameters, they just get included in the story and carry along in the usual way. But I didn't write this so that there are non-centrality parameters in there. Well, okay, so if we think of Cochran's theorem, there's my V, there's my V1, and there's my V2. So apply the theorem, and it says that V2, which would be sigma squares treatment over sigma squared, would have a chi-square distribution with degrees of freedom equal to, let's see, degrees of freedom equal to the difference of degrees of freedom. So n minus 1 what am I doing? Minus n minus k. Okay, get that right. And then those degrees of freedom become k minus 1. So that matches what's in the ANOVA table. And moreover, Cochran's theorem tells us that these two variables are independent. So now if we have two independent chi-squares, we can form an F statistic by the definition of an F random variable in the, again, on the last page of this handout there. And so if we take sigma squares treatment over sigma squared divided by its degrees of freedom, k minus 1, divide that by sigma squares error over sigma squared, that's the other chi-square variable, dividing it by its degrees of freedom. Now you notice these sums of squares in the numerator and then the degrees of freedom in the denominator give me what we call the mean squares. The mean squares are the sum of squares divided by the degrees of freedom. First of all, I should say, cancel out the sigma squared. It's critically important, of course, but that go away. And then in the denominator, I would have mean square error. So by the definition of an F distribution, this thing has an F distribution. It's equal to the ratio of the mean squares, and that's what we call F in our usual notation. So that's a derivation of the F statistic in the ANOVA table truly having an F distribution, and that those are the appropriate degrees of freedom. All right, so so much for that story. Let's see where we were at. I think I remember on page 4 that we skipped this number 7 about contrasts. And they're going to come up later on today, so let me talk about that for a moment now before we need to talk about it later. So on page 4, population contrasts. So basically in our problem, we have populations with mean mu1, mu2, through mu k. Okay. Now, we have k means then in our problem. If we form this kind of linear combination, the c's are constants. This is called a contrast when the sum of the coefficients there is 0. So for instance, if I had 3 means, I had mu1, mu2, and mu3. A contrast would be, for example, mu1 minus mu2, because the coefficients are 1, minus 1, and 0. That adds up to 0, so it's a contrast. Similarly, something like mu2 minus mu3 would be a contrast. notice how the word contrast is kind of natural here, because the difference between two things is a way to contrast them, using the word in its usual English sense. So this is a contrast because the coefficients are 0, 1, minus 1, and those coefficients add to 0. So no problem there. A little bit different type of a contrast might be something like mu1 plus mu2 over 2 minus mu3. The coefficients there are minus 1/2, plus 1/2, plus 1/2, and then minus 1. And those coefficients add to 0, so again, that's contrast. So this is an example, sort of a simple one, of what we might mean by a contrast. So in general, regardless how many means we have, if we form these kind of things to be of our interest, so long as the sum of the coefficients is 0, we can call them contrasts. Now, that's for the population. To get the corresponding sample contrast, which would be the sample estimate, notice I'm using the symbol with a hat over the top of it, sort of standard statistical notation, to talk about the estimate of a parameter, put the hat on top of it, signal the estimate. But you'll notice what's going on here is that I've replaced the mu's by their corresponding sample estimates and left the coefficients alone. So this is a random variable, this sample contrast. What kind of distribution does it have? Well, here's the statement right here. The y bars are normally distributed, and they're independent actually. So this is a linear combination of independent normal variables. It's again having a normal distribution. And the mean would be, substitute in for the variables, the means of the variables. And I've already got one copy of this here with me, so I'll have to just point here. It's this idea right here, number A3. You want the mean of a linear combination, it looks like that. And then the next line, if you want the variance of a linear combination, it's going to look like that. Notice how the coefficients are coming out as squares. And if they're independent, you don't have that covariance term. So that's what I'm thinking about anyway for this result that I'm looking at. So to get the mean, the expected value, substitute in the means of the y bars, and then we'd be looking at this first expression up above, which we call psi. And then for the variance, this kind of a thing, it's going to be the sum of the c squares times the variance of the y's. Well, so in this expression that I have here, notice that I've got the cej squared there. And then the variances are of the form, well, sigma squared over n, right? And so I've just factored the sigma squared out on the right side here to let it stay alone. So anyway, there's an expression, a nice usable expression for the variance of the sample contrast. We know the C's in any given application. We know the sample sizes n in any given application. And then we further know how to estimate sigma squared from the mean square error of the ANOVA table. So we can calculate this kind of stuff as we need to. Now something new that goes on next is called here the component of a contrast. The component of a contrast is defined, this is a definition, it's not a result, it's a definition, as the square of the contrast divided by its variance. Well, not quite its variance. We omit the sigma squared part of its variance in the denominator. Okay. So this kind of thing is a component, we call it. And then if we look at this component divided by sigma squared, we put that in there, this has a chi-square 1 distribution. It has a non-centrality parameter in this chi-square distribution statement. How do we get the non-centrality parameter? I said what you have to do is to substitute back in the formula for the expression the means of the variables. Okay? Well, for example, if it was true that the parameter was 0, then when you substitute in for psi hat, psi, you get 0. So when you have a 0 non-centrality parameter, that's just a central regular chi-square distribution. Now, on occasion, we'll have this coming up. Suppose we have two contrasts. Psi 1 with coefficient C's, psi 2 with coefficient D's. We say these contrasts are orthogonal if the sum of the n, c, d's gives me 0. Orthogonal is a geometric kind of perpendicular. So if we wanted to talk about geometry, we could somehow talk about how this is related to perpendicular vectors in k-dimensional space. But we don't need to talk about that. That doesn't help us to talk about that anyway. The key thing is, if we have two orthogonal contrasts, there's sample contrasts of independent random variables. So if you look at the ones that I was drawing over here, here's one. Here's another one. Are those two contrasts orthogonal? In looking at this condition down here, for my question, just assume these ends are all equal so that that factor is outside of the sum. So then the condition says the sum of the products of the coefficient have to be 0. Well, that's not going to work here, right? 1 times 0 is 0. Minus 1 times 1 is minus 1. 0 times minus 1 is 0. Add those up, get minus 1. 0. So these two are not orthogonal. Let's look at this first one up here, and then this bottom one down here. Are those two orthogonal? So one set of coefficients, I'll repeat it from above, is 1 minus 1 is 0, and then you see the coefficients in the last one. So multiply them together. 1 times a half is a half. Minus 1 times 1 half is minus 1 half. 0 times 1 is 0. You add those up and you get 0. Okay? So those two are orthogonal. So sometimes contrasts are orthogonal, other times they're not. All right, so much for that. Let's get back to our handout here then.
Excuse me.
Yes?
How do we use VSS for the contrast? Is it like that if we add VSSC to it, we get the total sums of squares, or how do we use it?
How do you use the sum of
The sums of squares for the contrast.
Oh, the component, as I call it, right?
The component of the contrast.
Okay. Well, actually, I haven't got any use for the component in this handout yet. So it's a detail that we'll worry about later. Okay? So don't worry about it for now. So, as I recall, last time we talked about this example on page 5, the ANOVA table, the confidence intervals for the difference between the means. And so let's continue on page 6, where we have example 2. So we're apparently molding plastic parts of some nature, which we don't have to concern ourselves with. and we have three different cooling methods in the process: a standard procedure, a new proposal A, and a new proposal B. And so we want to test out the cooling methods by getting some data. So here it says 15 plastic parts were selected, and at random, 5 of them were assigned to each of the 3 cooling methods. And we got the following data. So there's the data that occurred measuring the shrinkage. So we have 3 levels for this factor cooling method, and we have 5 observations in each group. So we would call this a balanced set of data. We have equal sample sizes here to deal with. So here's some of the standard things. The summing down the columns gives me the totals. Dividing each of those by 5 gives me the means. I have to calculate the standard deviations as well. Although in this example, I don't use those standard deviations for anything, but I could calculate them. There they are. And the overall sum of all 15 observations is over there, 365. So to calculate the ANOVA table, I begin by adding up the squares for all the data. There it is. Then I go to the column totals, squaring them and dividing by n. You get that sum. And finally put them together in our computational formulas. Sorry, it's getting too long. Putting those together in our computational formulas, sum of squares total is that sum minus that business. There it is. Sum of squares treatment is that sum minus the same thing, which gives me that. And then the sum of squares error is the difference between those two, giving me that. So I fussed around, calculated the 3 sums of squares for the ANOVA table. The ANOVA table comes out looking like this. Here's the sums of squares. The degrees of freedom are these. The 2 is k minus 1. The 14 is n minus 1, where n is 15. And then this has got to be n minus k, 15 minus 3. So there's the degrees of freedom. Mean squares, and finally the F statistic, the ratio of the 2 mean squares. So here's my main test statistic, the F test statistic. So to test for its significance for the hypothesis H naught, what's H naught? It's not even mentioned here, but it's such a standard thing that we just assume it's the usual one. The hypothesis that mu1 equals mu2 equals mu3. So anyway, we would go to the F table, find the appropriate 0.05 level critical value, 3.89. Our F statistic exceeds that, so our conclusion is reject H naught. Conclude the means are somehow different. So a little more detail about this example continues. Here's the distribution of the jth sample mean, for instance, and the estimates would be the 3 sample means. So mu1 is estimated by 20, mu2 is estimated by 24.2, mu3 is estimated by 28.8. And then here's the estimate of sigma squared, the other unknown parameter in our model. It's the mean square error. So from the ANOVA table, we see what it is. So if we start with those estimates, somebody might want to know, well, how accurate are these estimates? To answer that question, we turn to confidence intervals. That's what confidence intervals are basically for. So go back to the usual formula. Here it is, 12 degrees of freedom. And then calculate that out. I think what I did, I could see looking ahead, that plus or minus number must wash out to be 3.75. So here's the first confidence interval, here's the second confidence interval, and here's the third confidence interval. So that provides us some information as to how accurate those first estimates were. They're within 3.75 of the true values, at least with 95% confidence. Now let's look at some pairwise contrasts. So here I'm going to look at a difference between two sample means. Here's its distribution. The confidence interval formula is following it next there. The T number from the T table is the same one that was up above, so I didn't repeat it here. So plugging in the numbers that we know, we get plus or minus 5.3. And then here's the confidence intervals. mu2 minus mu1 is in that range. And quick glance tells us it includes 0. mu3 minus mu1 is in that range. And I'll just write there no, that doesn't include 0. And then mu3 minus mu2 is in that range. And I would say, yes, it does include 0. So to try to describe the conclusion in terms of our underlying method, that's what's left at the bottom of the page there. Label the three groups in order of increasing sample mean, and then underline the ones that are equal. And then end up with this. 1 is equal to 2. And we go on and say, is 1 equal to 3? And the answer to that was no, so I don't continue any further there. I drop down and start here and say, is 2 equal to 3? Looking above, yes it is, so I put a line there. And we're done. So there's a little graphic device to illustrate what we've concluded with these pairwise confidence intervals. I didn't do it on this example page, but if you remember the context for these three groups, 1 was the standard procedure, and then 2 and 3 were new proposals. So somebody might wonder, what about a contrast like this? Contrast the standard one against the new ones. Okay. So this is a contrast. The coefficients are 1, minus 1/2, minus 1/2, which adds up to 0 contrast. So we could be interested in some kind of inference for this contrast, if that was a question that made some sense to us. Do I want to compare the standard method with sort of both of the new ones lumped together? Maybe I do. Then I would focus on a contrast like that. Page 8. Another set of data, another example. All right, so these brass fittings are made on a cutting machine, and one of the things that's of interest in these fittings is their micro finish, sort of a measure of their smoothness. Okay? And basically, the feed rate is how fast do they push the rods into the machine. If they push it in really slow, maybe they get a smooth finish for the result. If they push it in too fast, the cutting is maybe a little more irregular and erratic, and they get a rougher finish. So anyway, this feed rate has some effect on the smoothness of the brass fittings. So here's what was done. It says, here's our data. So we see 4 feed rates, 20 being the current one under use, but 1 is smaller and 2 are larger than that to see whether we get better results. And then you see the data in each of the 4 groups. And the thing you notice about this data is that the sample sizes are not all equal. They're different. So what happens when we have unequal sample sizes? That's part of the message of this example. So we add up down the columns to get the totals. We divide by the number of items in each data set to get the means. So we have those and we have those, and we get the grand total of all 20 numbers. That's the total sample size. And dividing those two, we get the grand mean. So anyway, I want to calculate the ANOVA table. So again, my approach here in this example is the same as in earlier examples. Calculate that thing, sum of the squares of all the data. Then calculate this thing here. And we have to be slightly careful because the sample sizes in each column differ. So we have a different denominator in these kind of terms. For example, the first one would be this, let's see, 316 squared divided by 4. The next one would be 408 squared divided by 6. So notice how the denominator is shifting there as I go through those 4 cases. But anyway, you can check this arithmetic out on your own as well. There's the answer I got. And so put them together into our 3 sums of squares. And that work is done here same way as before. So here's our ANOVA table. And our key interest is in the F-test statistic. The critical value from the table are 3 and 16 degrees of freedom. Notice those are the right degrees of freedom. 3 is 4 minus 1. 19 is 20 minus 1. And the 16 is 20 minus 4. So they're following our earlier formulas with no change at all. So anyway, the degrees of freedom are 3 and 16. Go to the F table, look up the number, the critical value is there. And so our F statistic exceeds the critical value from the table. So our conclusion is to reject H naught. It doesn't even say here what's H naught, if you notice, but it's just implied to be the obvious thing. The H naught would be the test that the 4 means, the 4 population means are equal. And we reject that. So notice, as far as running that F-test, the fact that I had unequal sample sizes really didn't have any effect at all. The steps that you see here are the same as what you saw in the earlier examples, right? No major effect with unequal sample sizes. All right, let's finish up the example on the next page then. Here's the 4 sample sizes. Here's the 4 sample means. And sometimes with that information, people like to make a plot. So the picture would look like this. The values for the levels were 10, 20, 30, and 40. Notice how they're equally spaced. And that's important for what we're going to do next. And then I would plot the means on the vertical axis. So at 10, the mean was 79. At 20, it was 68, so that's a little lower. At 30, it was 57, a little bit lower yet. And then the last one, it's up a little bit, 62. So we get some kind of picture that looks maybe like that. And that's just a rough sketch. You could always draw a more accurate sketch to whatever purposes you need. But that would be a picture of the means. Good idea to do this in analyzing data when the categories of the factor are quantitative, like this, feed rate. So now, what people are interested in a situation like this is to say, well, I'm seeing a downward trend as I move left to right. I'm seeing some amount of curvature. Are those things that I'm seeing significant? Are they statistically significant? And so what they try to focus on is what they call orthogonal polynomials. So if you have four groups, these are the coefficients that are used in the orthogonal polynomials. They're derivable with some math calculations, which we're not going to go through. We'll just accept these as the standard coefficients. So for example, the linear contrast has those coefficients. The quadratic contrast has those coefficients. And the cubic contrast has those coefficients. And we don't have to go any higher than that, because with 4 points, you can fit 4 points perfectly with a fourth degree equation. So there's no error involved with any higher order polynomials. So using these coefficients, the psi hats are these. For the linear, it's minus 62. That is, use those linear coefficients times the sample means and add them up and get minus 62. Then here's this formula, which was in the variance, as you recall. And for those coefficients in the linear case, it comes out to be that. And then the what I call the variance piece is the square root of mean square error times that. So that gives me that. And then I'll repeat the same thing for the quadratic coefficients. And finally for the cubic coefficients. And I have all that stuff in front of my eyes to look at. What might I do with it? Well, one of the things we can do is to form a t-test statistic. Thank you. And that's what it does next. So this t statistic, say TL, L stands for linear, is going to be psi hat L minus 0 over the square root of its variance. All right. So notice the 0 there, because that's like the null hypothesis that we're testing. We're testing that the linear trend is 0. If a linear trend is 0, that means the line would be horizontal. So anyway, there you see it. You've got the numbers in the tableau above. So that t statistic is minus 3 something. Then for the quadratic, do the same ratio. There's the quadratic. For the cubic, there it is there. Now I see right here is the appropriate point from the t-table. And so when I look at these t-test statistics, the bottom one is not significant, the middle one is not significant, the top one is significant. So as far as these 3 t-tests would go, I'm only finding a significant linear trend. There's no significant quadratic trend. There's no significant cubic trend. So when I do that picture, where did it go? There it is. When I drew that picture for you on the other slide over here, this one, notice there was a bit of a curve here, right? That curve that we're seeing here, we're basically saying is random goings. It's not significant. There's no quadratic trend in this plot. There's no cubic trend in this plot. So that's random noise. So we would kind of ignore that. We would say the only thing that's going on here is that there's a downward trend somehow in this response. If instead of doing t-tests, we wanted to do confidence intervals, here's the formula for the confidence interval. Now it has the same pattern, notice, as other confidence interval formulas had for us before. Here's the estimate, plus or minus, number for the t-table. This is the square root of the variance. So to get the confidence interval, we have to know what this variance formula is. And we know what it is for these contrast type things. So we throw in the formula again one more time. So anyway, when I plugged in those numbers, I got these confidence intervals. So notice in these confidence intervals, the bottom one contains 0. So there's no significant cubic trend. The middle one, just barely, but it does contain 0. So there's no significant quadratic trend. And finally, I'll just put a no there. The linear confidence interval doesn't contain 0. So 0 is not a tenable value for the linear trend. It's not 0. So sometimes people prefer talking about the t-test statistics. And sometimes that's what our software gives us. Other times people prefer to talk about the confidence intervals. And you don't usually do them both. Usually you do one or the other depending on what your purpose is. All right. So finishing up here at the bottom of this page, this is an important enough issue to talk about. All of the calculations that we've talked about so far have been assuming the populations have equal variances. There was always just a sigma squared, one sigma squared, and we tried to estimate the mean square here. What if the populations have differing variances? What goes on then? So the situation might be we have one distribution that looks a lot like that. We have another distribution that looks like that. And then we have another one which looks like that. So these normal curves that I'm trying to just sketch here have somewhat different means, but they have very different variances. So what if our data is like this? So that's the issue that's being taken up here next. So notice in writing down these models, the variances are allowed to be unequal here. So we still have from our data the sample sizes, the sample means, and the sample standard deviations. Suppose we want to consider this hypothesis that the k variances are equal. Now, this hypothesis is tested with probably at least a dozen different test statistics, probably more like 3 dozen different test statistics. So there isn't one unique way to test this hypothesis. But the one that came to us first was called Bartlett's test. It's the one which was derived to be optimal if the populations were truly normally distributed. But we found with actual implementation that this test was very, very, very sensitive to the assumption of normal distributions. If the distributions for the populations strayed even a little bit from normal distributions, Bartlett's test fell apart. Just didn't perform very well. So in this day and age, it's really not recommended by anyone for use, although it's kind of a classical one that came down through history in the beginning. So this is the one that I'm going to recommend most highly for this class. Levine's test, more specifically the Brown-Forsythe modification. How does that go? Well, it describes it here. And you'll see how it's very simple to do. So it says, take the median of the data in the jth group, call it MJ, and calculate these absolute value of differences right there. So we take a basic data Yij, subtract off the median of its group, and then take absolute value. Call the resulting numbers x's, Xij. What do we do with these? Well, the next sentence tells it all. Do the regular F test for one factor and more using the Xij from the data. That's Levine's test. So this arithmetic right in here about adjusting the data from the median and then taking absolute values is something that we can have our software do, or we can even do this by hand. It's usually very quick. But then once we get these x's, then we carry out the usual F test. The idea intuitively is fairly simple. Suppose I try to draw just two sets of data. Suppose here's one set of data where the spread is like that. And below the line, I'll put another set of data where the spread is higher. Okay. So one sample has much less spread than another one. Now, if I continue, in the top sample, the median would be right there. Now look at the absolute value, look at the distances of the points to that median. And I'll try to draw them down here. So maybe 0 is there, and I'll get something like that, like that, like that, like that, and like the median, because I'm taking absolute value, right? So that washes that away. Now do the same thing for the other sample. The median of this sample is about there, and so these observations would have distance to the median, sort of like that, and like that, and then like that, and like that, and like that, and then like that. So these would be the x's. Okay. Now, what you're seeing is that now that I'm in these x's, their locations are different. The locations left to right are different. So I'm not interested in variation anymore on these x's. I'm only interested in where are their means, where are they centered. These x's are centered sort of about there, and the x's in the bottom sample are centered sort of about there. And there's a discrepancy there. There's a contrast there, which I'm trying to pick up by doing the ANOVA F test. And the ANOVA F test is not correct for this kind of data. The ANOVA F test was derived to be correct for normally distributed data, and these x's are not going to be normally distributed. That's pretty much for sure. But it turns out that just by luck, I suppose we could say, the F test works pretty well in this context. And it's been studied quite extensively, mostly in simulations, because the theory is too difficult. The theory just breaks down when you try to derive, well, what would be the correct properties of doing this kind of a test? Calculate these x's and then do this regular F test. What would be the properties of that F test? Well, it's too hard of a problem. Nobody knows the answer. So in those kind of circumstances, what statisticians nowadays can do is run simulations. They can generate data, 10,000 times and see what's the result of this test under this circumstance, under that circumstance, and so forth. And it turns out to pan out pretty well. So the Leeds test is the one I'll talk about most frequently here in this class, but I think it's the one that's most widely used in actual practice as well. So going back to the data on the cooling methods, where there were 3, here's the data again. The medians of these 3 columns are these numbers, 20, 25, and 28. And you can almost spot them by eye, because there's 5 numbers, the median would be the middle one. So there it is in that group. There it is in that group. And there it is in that group. Just an accident that those medians happen to be the second entry in each column. But there's the medians. So you subtract the medians from the data. And for example, in the first column, you get -4, 0, 2, -4, and 4. With an odd number of numbers in a column, I'm always going to have a 0 in these differences, right? Throw the 0 away. Throw the 0 away. So I wrote the resulting data down below again. These are the x's. Throwing away the zeros. There was a 0 in each column. So now it says do the usual one-factor F test. One thing I didn't say, and I should call your attention to it back here. In running this test, this Levine's test, bump up the significance level higher than 0.5. Don't run it at 0.5. So Stoline's recommendation has always been to run it at level 0.25, which he has gleaned from numerous readings of other statisticians about this kind of an issue. So I just simply say, without further ado, run this test at significance level 0.25. So I took this data into Minitab. There's the Minitab commands line. There's the command that I used. Here's the ANOVA table that Minitab produced, and the p-value for the test is 0.45. This is greater than 0.25, so we would accept H0. The H0 here is of equal variance. Right? Okay. All right, well, we're out of time today, so let's just stop there, finishing with that example. There's one head, half a page left here to talk about next time, and then we'll start a different detail. Okay?